Okay, it's time to begin. For people who maybe can't, maybe counting, no, I have not graded the exams you took this morning yet. Today we're going to be doing simple machines. So, simple machines are devices that should make doing a job easier in that we can do it with less force. So the goal of a simple machine is, that's not an E, less force to do work. We were supposed to introduce work last week, but we haven't yet. So I have to explain a little bit about what work is. Now some of you might say, oh, I know what work is. I used to work in the dairy, and I would get really tired, and that was work. It is a definition of work, but it's not the physics definition of work. And in fact, the definition we're going to use here is the definition for what we call, quote, mechanical work. Mechanical work is a work that we do on something that changes it. And the definition is work is equal to the force applied to an object multiplied by the distance it moves parallel to that force. So a simple example might be, I have this weight here in my hand, and it's not moving. How much work am I doing? None. I'm doing zero mechanical work. I have to be clear on that mechanical work because my muscles are exerting a little energy. There's using a little energy. And work is a conversion of energy process. So I have to be careful and say mechanical work. So I'm doing no mechanical work because the distance it's moving is zero. So let's say instead of having a distance moving to zero that I walk across the room like this. Now am I doing a mechanical work on it? The answer is still no. And the reason is the directions. Notice in the equation up there, that little, looks like a number 11, that means parallel. The distance has to be parallel to the force. My force was upward, but the distance moved was horizontal. Because the distances were perpendicular to each other, there was no work. Now if I take the weight and go like this, then going from this height to this height, what direction was the force that I applied to this weight? Up. What direction was its motion? Up. In that case, I did a work. And it was a positive work because my force was the same direction. Now, if I start up here and I bring it down, what direction was the force that I put on this weight? I still put an upward force. Gravity was making a downward force, right? I did an upward force. What direction did it move? Down. So my force was up and the direction it moved was down. When they're opposite directions, that's a negative work. So I did a negative work on it, bringing it from here to here. Now, I don't recover that energy. My body doesn't bulk up. We can't go to the gym and have one person lift a weight and then another person lower it. And the one person gets strong and the other one gets bigger. You know, it's not the way things work. You know, one person just gets more energy. The person who puts it down each time gets more energy. The other person gets strong. It's not how it works. Because your muscles are having to do energy conversions both when you're going up and going down. In fact, on the lifting routine my son and I are doing, on Fridays we do negative lifts. That is, got the bar on the weight rack, somebody helps you bring it out here, and then you lower it to your chest, and you try to push up, but then the other person picks it up off your chest and puts it back. Just on a principle idea, why would that be part of our lifting routine?
Still work going down.
It's still work going down because I am still applying a force. And in fact, those negatives, I have to do everything I can because unless it's accelerating downward, if it's coming down at constant speed, the goal is that it's not dropping and bouncing off your chest, right? If it's coming down at constant speed, its acceleration is zero. And Newton's second law says my upward force is the same as the downward force of gravity. So I'm actually holding that weight for a short time. Even though I can't push it up, I can't overcome it, I can keep it from falling on me and crushing me, and I'm getting the absolute maximum out of my muscles. Yeah. My boy's loving the fact that we're getting buff. Yeah. Okay, so work. Work is that force doing something, making something move. Something that is often confused is this weight is sitting on the table right now. Is the table required to do any work to keep it sitting there?
No.
The answer is no. Is the table putting a force on it to keep it there? Yes. A lot of people get those two answers confused, and they think about, what if I was holding this? Would I be doing any mechanical work? No. Would I be doing a force? Yes. But then you ask, so do I get tired? And the answer is yes, I get tired eventually. Because my body is still having to expend energy. And they start thinking that maybe the table has to expend energy to hold it here, and so there's only finite time before the table's done and gives out just like I would. And that's not the case. Because the table does not have to constantly have chemical reactions occurring to convert energy to hold it there. It's just strong enough to hold it there. But our bodies, we have to actually have the muscles do work. Okay, everybody understand what this mechanical work idea is? Once you understand the mechanical work idea, then we can talk about the simple machines a little more carefully. When I was a young lad, 14, my dad thought, well, every 14-year-old needs to have a non-working car so that he can make it work. So we went out and we bought this $200 Toyota Corona. The thing was so messed up, we never knew how old it was. It said that it was a 1969 model, first sold in 1964. Yeah, clearly those two don't work together. We didn't even know. I mean, we just guessed. So one of the first things we had to do, take it home, and Dad says, okay, son, here's a birthday present. Some end wrenches and a socket set. Now you take that engine out of there, you take the engine apart, and then we'll clean it up and we'll put it back together and make it work. So I mean, my dad helped me a little, but I did a lot of it autonomously. And one of the first things you got to do is, well, you got to take the engine out of the car. All of this lead up to you got to take the engine out of the car. So to take the engine out of the car, my dad brings home a thing that's about this tall that has a bunch of pulleys on it and chains. And so we put a chain around the engine or something like that and pull on the chain, and it pulls it up until it's a little bit tight. Take off the for whatever bolt it was that holds your engine to your car. And I was shocked that I was able to easily lift the engine out of the car. Now keep in mind, I was 14. At that point in my life, I could probably bench press like 135, 150 pounds, something like that. Right? There's no way I could have picked this thing up. So how did I pull it up? By using the chains and pulley system. A mechanical advantage. The chain and pulley system is a kind of simple machine. Now, we have studied pulleys in the past, and so I'm just bringing up a blank page to go to here. If we look at pulleys, here is a pulley, and I am going to put, well, I'll put a second pulley up here. This pulley is going to be tied to my ceiling. So there's the ceiling. And then I'm going to have a blue cable that goes like this. And then I'll have wee little Richard down here pulling that down. Now first, the simplest thing of all. If I am pulling with some force force sub P for pull, how much is the rope or chain pulling on me? Should be the same because I'm assuming I'm in equilibrium, that I'm not accelerating things. So if I'm in equilibrium, it's going to be the same. So it's going to be pulling on me with that same F sub P. Now that force gets transmitted through the chain or cable. What do we call the transmitted force? The tension. So there's a tension here that's equal to the force pulling. Now let's come down to this pulley here from which hangs the engine. What forces are acting on that pulley? Okay, the two parts of the chain. There's one coming up here and one coming up here. And so I'll put force of tension here since I'm no longer connected to me pulling. I have those two forces of tension, and then there's one more force that's acting on the pulley. What's the last force? The force of gravity on the engine. Now, if I'm in equilibrium, if I'm able to easily raise or lower it and I'm not accelerating it, sum of the forces is equal to what value? Newton's second law says sum of the forces is equal to mass times acceleration. If I'm not accelerating it, that's going to be equal to 0. So now I just look at this and I say, the sum of the force in the vertical direction, I had 2 FTs going up and 1 FG going down equal to 0. So that means that the force of gravity is equal to 2 times the force of tension, or the force of tension is equal to the force of gravity divided by 2. So now with what I've worked out, how hard do I have to pull to lift my engine with this system? Only half the weight of the engine. Now it seems ridiculous that I can lift the engine by only applying half of that force, but the fact is that force is being applied 2 different times. Now if I lift the engine, if I want to raise the engine 1 meter, how much chain is going to have to move? 2 meters, because I have to go up 1 on each side. So the distance I have to move is twice as big, but the force is half as big. How does the work compare? Half the force and twice the distance. Work is blank times blank. Force times distance. So I have twice the distance times half the force. It's the same. So the work I do is the same. I'm not getting extra work. But what I am doing is getting the work done with less force required. Now, of course, I did not use half of the engine's weight to lift it either. Our system had like 3 pulleys down at the bottom, which means that we had 6 ropes coming up, 3 on each side. So that means I only had to do about 1/6 of the force of the engine to raise it. And it was real easy. I was shocked. Didn't make sense to me at all because I didn't understand physics then. That's a simple machine, and you can see the utility of that. Here's another simple machine. We have all been involved in moving, right? You move stuff into the dormitory. Well, when you're putting that moving van, you have something like let's say a refrigerator. And you want to get it from the ground into the back of the moving van. And you don't have a lift gate. What's the easiest way to get it from the ground into the back of the moving van if you don't have a lift gate? A long board. A long board or a ramp. A ramp is a type of simple machine. So let's look at that. Here's a ramp. We have some angle theta. And I have my refrigerator on this ramp. Now let's assume there's no friction. We're on a dolly or something, so we don't have to worry about friction. What forces are acting on this refrigerator? Okay, there's a normal force. What direction is that going to point? 9 degrees to the surface. I want to make sure people didn't say up. So I have a force normal like this. What else do I have? Force of gravity, that is down. And then there's going to have to be one more force, as you had on the test today. If we just had, there's no friction here. If we just had these two forces, what would happen? It'd roll down the ramp. So what do I have to have for my third force? I've got to have my force applied, somebody pushing it up. Now the question is, if I'm going to move with no acceleration, just constant velocity, how does this force applied compare to the force of gravity? And to answer that, I can use Newton's second law. Sum of the force vectors is equal to mass times acceleration vector equals 0 if we're not accelerating, if we're just going at constant velocity. Well, if I look at that, I have the force applied like this. I have the force normal like that. And, well, my lengths don't work out here with my picture. So the force applied like this, the force normal like this, and then the force of gravity like that. When you add vectors, you add them tip to tail, and if they add up to 0, it has to come back to where it started. With the directions, normal was, as Andrew said, 90 degrees from the slope, and my force applies up the slope. So that means this angle here is 90 degrees. I had an angle right here that was theta, and that angle being theta means this angle here is also theta. And so I can look right now and I can say, well, the force applied and the force of gravity are the opposite and hypotenuse signs of that triangle. So using trigonometry, sine of theta is the opposite of hypotenuse. Or in other words, the force I have to apply is the force of gravity times sine of theta. So if theta is a small angle, like let's say theta is 30 degrees, then sine of theta is 1/2. So if my ramp is at a 30-degree angle, I only have to apply half of the force, or half of the weight of the refrigerator to get it to go up the ramp. If I make it steeper, I'm going to have to apply more, flat or less. But that's, again, a simple machine. Now we talk about these and we measure what we call the mechanical advantage. Mechanical advantage is how much it helps me. The actual mechanical advantage, we call that the AMA for actual mechanical advantage, is equal to the force I had to move, so the force of the load, divided by the force I had to apply. So in my example of the pulley system, the force I had to apply was force tension, and the force of the load was force of gravity. So if I put those two into my equation for the actual mechanical advantage, the load Fg divided by the force applied, which is force tension or force G over 2, that's equal to 2. So the actual mechanical advantage of that was 2. The theoretical mechanical advantage would be the ratio of the distances. Why are the two not necessarily the same? Because the distances is going to be the same every time. But if I have frictional force involved, remember I said no friction? If there is frictional force involved, well then that's going to affect the forces. So the actual mechanical advantage will vary even though the theoretical should be fixed. If we come down to the inclined plane then, the name for this machine is called the inclined plane. Its actual mechanical advantage would be the force of the load, once again, force of gravity, divided by the force applied, and the force applied was so the actual mechanical advantage is 1 over sine theta if there's no friction. The theoretical mechanical advantage I would calculate by relating the distance that it rises to the distance that it moves up the ramp, which it turns out is also sine theta for the relationship. So those are a couple examples. Now the one you're going to do in class today is the third example. So what's our third example of a simple machine? It's going to be a lever. So here's a picture. I didn't take this picture myself. Of our setup. So you're going to have a little platform. You can see that Colby already has this set up. This is your platform. You're going to have a meter stick. And you have 3 of these. One of them has no hanger on it. That one goes at the center. You want to put that on the center so that these little knife edges are on the top part of your meter stick. And then you put it in here. Now I'm putting this right at the midway point. In theory, you would expect it to balance there, right? In practice, it may or may not. Clearly, the center of mass is not at the middle of this thing. So you need to take it and adjust it until you get it so it's balanced. This one is not close. Okay, that's pretty close. It's not perfect, but it's pretty close. Now remember I said that you want to put it so the knife edges are on the top side. Okay, that's pretty darn good. Maybe a little overkill. Pretty good though. Watch what happens if I flip it over so the knife edges are on the bottom. It's now just resting on these things. Why is that? Stable versus unstable equilibrium. If the knife edges are up high, then the center of mass is down below them, and it will try to balance with the center of mass directly below these knife edges. If you tip it a little bit, the center of mass actually goes up, raises the energy. A similar thing occurs with a person standing. If I stand like this, I can stay standing like this, but I'm not very stable. If Bronco fan came and tried to push me over, what would happen? I would fall. I would go boom, because I'm not very stable there. If, on the other hand, I stand with my feet wide apart, and Bronco fan comes, he can push as hard as he wants. I ain't going anywhere, right? It's the same idea, stable versus unstable equilibrium. So make sure you have it so the knife edges are high on that one. So you have that one balanced. You need to take these two things and measure the mass of each one. You need to decide which one's number 1 and which one's number 2. Most of them look different. So you can say like, okay, this one has a flat bottom. This one has a ridge on the bottom. Flat bottom will be number 1, ridge will be number 2. I can keep them separated that way in my mind. I need to measure the mass of each one of these, so you bring out the triple beam balances. Remember to zero them before you start. Measure the mass of each one. How many decimal places should you have when you measure the mass of these things?
2.
That's right, 2. So you're going to measure these, and you put those measurements in your data table. So let me jump to the data table. First, that. Oh, sesame. So in our data table, you put the value you measured for hanger 1 and for hanger 2, and then make sure you put your uncertainties in there. If you don't put in those uncertainties, Toussaint is going to have to take off some points. You also need to record what the position is here where I have this balancing. Now, how do I determine that? there are two different kinds of indicators. I'm actually going to take a picture here. Okay, I just put that on top of everything. Perfect. Yeah. I put that on top of the data. Okay, let me move it so it's not on top of the data table. There, I'll leave it up there. Yeah, a little more. Okay, so when I look at this, the way to read this one is to read where this indicator falls. So I can see, okay, this was 50 was right about here. This here is 49. It's a little bit left of 49, so I would read this as, well, 48 point, and then I got to go 9, and I estimate one more decimal place. So 48.9, what do you say? Okay? I heard 5, so I have 48.95. So that's what I would record right here. But then I need an uncertainty. How big is my uncertainty in that measurement? Okay, somewhere around 0.03. 0.03, 0.05. It actually depends on which one you have. The other kinds of indicators, okay, this one here that they have is the other kind of indicator. Okay, you're supposed to put this one right at 10. So I'm doing as best I can. Whoops. All that work to get it loose, and now I can't tighten it. You'll want to get a different hanger. This one here won't tighten. It just slides. We do have one more, so let me find somebody else who has that kind. Okay, this one's that kind.
Thanks for keeping it.
Thanks for keeping it. That's the way it is. Friends. Sharing and sharing alike. Okay, so this one here, I'll take a picture so you can compare the two. Come on. It's thinking. Okay, I can't really, well, now I'm covering the data table. I'll erase it maybe. So here's the second kind of indicator. This one here, you just read right on that edge. And so that's as close as I can get to 10.00, the way I put it on there. If you think that's 10.01, that's your prerogative, right? That's why we have the uncertainty. So you read them that way. Two different kinds, you have to be able to read them both ways. Down to the data table. I've got my masses and positions marked. There's only 2 trials in today's lab. So Hassan and I finished really quickly with our first trial. We didn't do the second. The first trial, I'm going to put 50 grams on this hanger here at 10 centimeters from the edge. And then I'm going to take my other hanger and I'm going to put 100 grams on it and find where I have to put it to balance. Okay, so I get it balanced, or close. Now I need to record my data. So what was the position of this one? It was just 10 centimeters. So it better be like that for everybody there. Now the position is what I wrote. The distance is the distance between this location and that location. So how far is it from 10.00 to 48.85? It'd be 38.85, just subtracting them. So this distance here for my measurement is 38.85. Notice I have uncertainties. And then I have the mass. Now this mass here was 50 grams, right? But you also had to measure the mass of the hanger. So this mass here is not 50 grams. It's going to be 50 plus whatever the mass of the hanger was. So let's say, I'm just going to make up a number. I made up that number. It's not correct, but it's just a number so we can do stuff. Now I look on the other side and say, where is this one? Now I'm not going to put the right number here either because I don't want these ladies to, just be able to say, hey, we're halfway done with the experiment already. So I'm just going to say that position is 73.50 centimeters. Notice I'm putting my uncertainties in position. The distance would be going from 48 point, actually is that a 9.5? That is a 9.5. So that's 38.95. It'd be going from 73.5 to 48.95. So that would be going 24.55. And the mass here, 100 grams plus the mass of hanger 2. So I'm just once again going to randomly put 112.58. So there's my first set of data. Now, what is wrong about my data? Number one is that I intentionally used the wrong value for this. Number two is that I don't know what the masses are of the hanger, so I just made up numbers. When you do yours, you need to do it correctly. I'm going to move this now so these ladies don't say, he did it.
Distance from here to the center?
Distance from here to where this is. Okay. So that's why we had this number recorded, because that's how we find the position. The distance is the distance from there to there.
Wait, so what one's position again?
The position is what you read on the meter stick.
Oh, and the distance is from the center to
From this center balance point. Yeah, not the center of the meter stick, but the balance point. Because on theirs is more than a centimeter away from the center of the meter stick to the balance point. Now we need to find the theoretical and actual mechanical advantages. The theoretical mechanical advantage is based on the distances. Easy way to do this, do the bigger distance divided by the smaller distance. So in this case, that would be 38.95 divided by 24.55. So I put those in my calculator. I get my number. It's somewhere, I don't know. It's a number. It's bigger than 1, less than 2. It's about 1.6. Make sure you have 3 digits on that number, okay? Then my actual mechanical advantage is going to be the ratio of the masses. So I just take the bigger mass, 112.58, divided by the smaller one, 62.51. That's like 1.9 something. So I have my actual and my theoretical, and then finally I'm going to calculate the efficiency. The efficiency is the actual divided by the theoretical. So I would just take, in this case, 1.9 divided by 1.6. I'd put the actual values in and get the number there. Since I did all these numbers kind of made up, there's no sense to this.
You couldn't have efficiency above 100%.
Well, with this here, the efficiency should be exactly 1, and it's experimental error that makes it not 1. Experimental error can go both ways. But yeah, you're right. In real life, you're never going to get a higher actual than your theoretical. So you're going to calculate what that efficiency is, and then calculate times 100%, so you have it in a percentage, like 98.3%. And then you have a second trial to do. Repeat the measurements above, except for place 200 grams on hanger 2 So hanger 1 is going to stay exactly the same. Hanger 2 is going to be 200 grams. You'll have to find a new position for hanger 2. And you'll repeat the measurements. And then you have a couple questions. And then the lab will be over. Any questions? All right. Then go ahead and have at it. Yes, sir.